Login accepted.
Good morning, everybody. I would like to welcome you on my talk today. I will be talking about reactive programming a bit. I came here from Helidon team directly. I am the architect of Project Helidon, which is being created at Oracle as an open source microservices framework. So what will I tell you today? I will do a very short introduction into what is Helidon. I represent it, so I want you to know what we are talking about. And then I will dive a bit deeper into the reactive engine that we use, show a bit about our Reactive Webserver, the messaging opportunities that you have with Helidon, and reactiveness, and a few reactive goodies at the end. And if the time permits, I will talk a bit about the future, which may be a bit of a surprise, especially when it comes to reactive programming. So, let's go. Let's start with what is Helidon. As I said, we write a framework for writing microservices. It's actually a set of libraries that you can use separately. You are not required to use the whole framework. We are open source under Apache 2.0, which is a very permissive license. And we are built on top of Netty as the underlying HTTP server. I have added the brackets there quite recently, and again, I will explain that at the very end, why I said for now. It's cloud native ready. We support all the usual things like health checks, metrics, tracing for observability, REST endpoints so you can expose your services, and all the things like fitting right into your Kubernetes cluster. You can also deploy it on your hardware. You can run it on your laptop if you choose to. It's a standalone web server with a lot of features. We also support Graal VM native image if you are interested in that part, which allows you to build native executables from Java programs. In Helidon, we have the basic 3 layers. There is the web server, which in our case is backed by Netty. There is the Helidon reactive code, and there is something we call Helidon microprofile. Microprofile is an Eclipse specification that covers mostly cloud-related technologies, like I said already, metrics tracing, and allows you to build declarative applications based on CDI and so on. In our implementation, most of the features that we have are built on top of the Reactive Webserver and Reactive Helidon, even the microprofile ones, so it's all backed by the same server. Just a very quick example how it looks when you use these, what we call flavors. In Helidon SE, you code everything. When we started this project, we decided that Helidon SE will be the no magic approach. So there is no use of annotations at all. Like there is 0 annotations in the code. What you code is what you get, which obviously requires a bit more from the programmer, but on the other hand makes it much clearer to understand what the program is doing. Opposed to that, we have Helidon MP, which is the classical inversion of control framework, where you annotate your classes and magic happens. So the example here is a JAX-RS service, and of course it's blocking because JAX-RS is designed as blocking, so you just return your hello world. In Helidon SE, everything is non-blocking and reactive. So if you just want to send a response, you send it when you are ready. If you want to process something asynchronously, you use reactive streams. We'll get to that. I will skip this. Just a very quick, this is a set of features in a microprofile. Just want to show that there is a set of features, the blue ones, which are prescribed by the specification. There is a set of features which are the red ones, which are actually Jakarta Enterprise Edition features. And there is a few other features that either are additional from microprofile or we add them as Helidon. you will see very similar set of features in Helidon SE. So, the main reason why this presentation actually exists is this whole thing is blocking. And blocking has its own problems. So let's talk a bit about reactive, and we will get to the problems later. So again, few features. The ones that are highlighted green, we will talk about those today. We call it the danger zone because reactive programming has one disadvantage. It is hard. And it's hard to make it even easier. Like, you cannot make it easy, but it's even hard to make it usable by normal people. So if you go into this space, you need to have a good reason for it. One of the reasons may be requirements on things like memory footprint, disk space usage, and startup time, where obviously the smaller the framework, the better numbers you get. By the way, the numbers there, they were measured on some Windows bed machines, so you know, it's not like generally transferred information. On this computer, it starts in something like 20 milliseconds. On some computers, it can be faster or slower. It's really to compare with our MP. So what is reactive? Why does it exist? That's the basic thing. So this is the amount of data that is being processed worldwide. I don't care about the numbers. The real important thing is that as the years go up, the amount of data that we need to process is increasing, and it's increasing a lot. And when you go with the classical blocking approach, where you basically have a thread that wants to do something, and let's say that the main thread is my application, and the thread 1 is something outside of my application, like I'm calling an HTTP service, or I am querying a database. These are the most common things you do in your services. You need to call other services, you need to call some blocking storage. When this happens in your usual JAX-RS application, your current thread is blocked. So you have a very good and ready platform thread running in your JVM, and it's doing nothing. It's waiting. And this is obviously not very good if you need to process a lot of data, because as soon as you do this 100 times, depending on hardware obviously, 1,000 times, your hardware will die. There's just not enough resources on your hardware to actually execute this. So reactive came into being. We found out that we cannot block our threads. This is actually copied from Wikipedia. So the real thing that is important from reactive is you do not block your threads, and you get the data when you can process them. I think that's like the core of the problem. There is a reactive manifesto, you can read it, that actually describes this problem much deeper than just saying these 2 sentences. And what is really, when it comes to the implementation, what does it mean in Java when I say you do stuff when it's ready and you are non-blocking? This is implemented through one interface, which has 4 inner classes. This was introduced in Java 9. It's Java concurrent flow. And the API consists of a publisher, and publisher is basically a source of data. So if you have your database and you do a select, the result set that you get can be your publisher if the database supports reactive. And it basically feeds you data when you want to. So I say, please give me the next 5 records, and the publisher will send you on next, on next, on next, on next on your subscriber until it does 5, and then you may request additional ones. Sounds great. Publisher is the easy part. Subscriber is a different story. Subscriber needs to request the data and needs to process them, needs to react on errors, needs to react on cancels. Subscription is the means where you tell the publisher what you want to do. And processor is just a merge of those 2 interfaces. So processor is a subscriber and a publisher at the same time. And it does something to the data so your stream can continue. Now I have the next slide. It's a trap. It looks nice. You feel like you understand the problem, but then you start working with it, and you realize that writing a publisher or writing a subscriber is incredibly complicated thing. You know, it has just 5 methods or something like that on the subscriber. It has 1 method on publisher. It's not that easy. You need to be aware of which threads are doing what. You need to be aware if you can request the next data within processing of the previous data. There is a set of TCK tests that make sure that it all works. So one thing, never ever implement these. This is something for the frameworks to do. You want to be the user, and as a user, you will basically see publishers, and you will see the reactive operators, reactive stream operators. There are a few implementations of these. Helidon is one of them. And let's see what I just said, what it means that you don't want to implement them. So we will look at the reactive engine itself. So our reactive stream operators depend on the concurrent flow. So we are not implementing anything else. If you want to use some other reactive streams, there are usually libraries that will allow you to switch from the Java util concurrent flow to others. So that's the base thing. We implement flow.publisher. We depend only on our common module. There is no external dependency. The main 2 classes that you may be interested in. First one is multi, which more or less equals a publisher. So a multi is a promise of future stream of data. The second class that we have is a single, which is a narrowed down publisher. That's a publisher that promises a future stream of exactly 1 record. So you know that this will be a single result. Comparison to the Java APIs, this is very similar to completable future. So you know you will get 1 record of your publisher. The reason why we use these 2 and they both implement publishers is because your APIs can utilize this. You have the same APIs, you can reuse your APIs regardless whether you know that you get 1 record or multiple. So here is an example why you don't want to implement your own subscribers and publishers. If you use a multi, and here I'm creating a multi from just numbers, a stream of numbers. But in practice, you would get this, as I said before, from a database, from Kafka, from some other source of your reactive data. And you can use the operators to modify this publisher, to basically modify the stream of data, and eventually do something with it. And obviously, this example is wrong. There is this nice await step. If you do await, you are just breaking everything. You are blocking, you are waiting until it finishes. I wanted to show it in the example so you can actually system out print line after it. You could also add the system out print line into your stream. So here you can see that we are doing limiting the number to 3 things. We are mapping it to another type. And then for each of them, we are computing something. And this is a very good example. You would do something like that in real life. You get your data, you want to map them to JSON. You may want to create an array out of that, maybe collect it in memory if it's the desired solution, or maybe for each JSON object that you get from your database, you actually want to send it over the network as a JSON stream. And that's exactly what this allows you to. Now, one thing that you need to be aware of, and this is true for any reactive implementation and for any reactive server, you cannot block. So in case, here in the for each, you actually want to call a service, you cannot do it the old way. You cannot just say, give me an HTTP request, I will wait for the result here. No, you need to use a reactive client that will return you some kind of a promise. So either a completable future or a publisher of its own, and you need to join these together. And I will show an example of that as well later. Single, as I said before, single is very similar to multi, it's just a single value. And here you can see this is the correct usage. So instead of waiting for the result, I say, do something when this is over, when you complete. Here is a list of operators. I will not go through all of them. It's just to show that there is a lot of things you may want to do with your stream. You may be reminded with the stream API in Java itself. There are actually similar things. The only difference is that this is a promise of some future results where the stream in Java are actual current results that you get immediately. So operator chain, we can see that this is too I will not go through this. Great, now I'm getting an update. I'm sorry, I will just need to move it away. You must love your corporate IT, which delivers updates in the middle of a presentation. Okay, I call it the bragging section. This is a performance comparison of implementations. It's very small, and I really don't want to go through it too much. It's just comparing SmallRye, Helidon, and Mutiny reactive streams. We win in most cases. Obviously, this depends on which version you look at, because everybody is improving over time. One of the good things for us was that actually David Carnock has participated on implementation of Helidon reactive streams, and he's the guy to go to when you need this done. So it was very helpful, and we can actually beat in most of these benchmarks. So that was an introduction to reactive streams. As I said before, you get a stream of data in the future. You can do something with that data as it comes, and when you finish doing something with the data, you treat it either by collecting it or by sending it somewhere else. Now, Reactive Webserver is one of those somewhere else where you can stream the data. It's also the source of the data if you are getting a request from a remote service. So let's have a look. And again, we can see the await used here. That's actually part of our APIs. When you start a server, this is happening in your main thread. So I'm not afraid of using await unless you want to start 25 servers in the same JVM. You can just block the main thread. Nobody cares, really. So I'm creating a server, and it's using something we call routing. This is actually influenced by JavaScript. We looked at Express. We quite kind of liked the way they do routing in HTTP, and we implemented that in Java. So in this case, we are creating a reactive route that will just send hello world. Not much reactiveness here. It's you don't really see it. I will show it in an actual example in the source code. So let's switch to IDE. Let's stop presentation mode. Okay. Now let's switch to IDE. Or not. So the fun part, when it shows a different screen than you want it to show. Wow. So I will have to work on the remote screen here. Okay, so I will start with something really small, so let me make it bigger. Can we see it now? Great. So first thing, I want to show what we implement. So multi implements a publisher, and of course it's a multi. Now there is the to-do, and that's a very important thing. In most reactive stream operators, you are not allowed to reuse the instance that you create. So if you create a multi, then you send it to one method that modifies it, runs a stream on it, and then you send it to another method, you'll break it. It will not work. So you always, if you process something, you always need to get the result of that process and use it later on. So in this case, if I just created a variable with the multi.just and then sent it to both of these methods, the second method would do nothing, because the multi is already consumed, and you are done. So let's have a look on why we created this. So if I go to the publisher, you can see that I am using the flow.publisher. This is coming from Java util concurrent. I will just highlight it. So this is the actual JDK implementation, API, sorry. And now if you go on publisher and you ask your IDE to autocomplete, you will find out there is just a single method, and that's subscribe. So let's say that I'm a new Java developer, I want to use the Flow APIs. Let's go there. So I will do a new subscriber. And you say, okay, let's do new flow.subscriber. And suddenly you need to implement a bunch of methods, and you need to understand the contract. And as I said before, the contract is complicated, like way too complicated. So you probably don't want to go this way. So how do I read these values and do something with them? So I will just remove it because I want to run this program eventually. So I will use my multi interface, which is coming from Helidon. And here you can see I'm doing a mapping. I parse an int from my stream. I make sure that it's an even number. So I'm doing a logical AND on number 1. So I filter out all those that end with 1, which are odd numbers, and then I just print them out. If I was doing this using a subscriber, I would spend probably half of a day of work to implement all of that. Now, I said that there is one feature of the streams, which is they are non-blocking, but they are also reactive in the terms that there is back pressure. I haven't mentioned that word yet. Back pressure is one of the most important things here. That basically means that you will not read the next value until you can process it. So let's imagine that this system out print line was some operation that takes time. You could actually design it in a way that you deliver the next record only when you actually process the previous one. And that's making sure that you do not request the next value, and if you don't request the next value, the originating stream will not send it. And this can actually be achieved all the way across network. And again, I have a database which supports reactive programming. It gives me a publisher of data. I have a web server that reads this from this database, and I have a client somewhere sitting on the internet that wants to read from this web server. If reactive implementation is correct, then you only read the data from the database when the client can read the data from the network and display it. And if anywhere on this chain there is a delay, something is blocking, you cannot read the data, you didn't yet render the data, so you are not interested in the next 10 records, the database is waiting. And this is absolutely critical for reactive implementations to work correctly. And that's one of the reasons why there are not that many implementations in the world, because, as I said at the beginning, it's hard. And even companies that came up with these ideas, like Netflix, only use it for the critical systems that really require this amount of concurrency. And for the less concurrent systems, they switched back to blocking APIs because it's much easier to maintain. So that was multi. Now for single, it's actually a bit more than for multi. So first, it can be used as a publisher, so I can call the publisher as well. It can be used as a single, where I can wait until I get the single result. And it can also be used as a completion stage. And this is the part where I said that it's a promise of a future result. And completable future, which actually implements completion stage as well, is exactly the same. You are expecting some future result, exactly one. So we decided to implement completion stage. This is, by the way, one of the things that we do in Helidon, and I think that nobody else does it. And the reason why we do it, it helps you work with these future promises that are not really a publisher. And you can find out in a lot of reactive APIs, you will get a publisher of, for example, you request a connection from a database, and you will get a publisher of connection, but you don't care about the publisher. You care about one connection that you need to work on. And the API promises exactly one. So why would you use a publisher? That really doesn't make sense. So that's one of the features that we added to make your life easier. Now, if I run my application, we can see that I get the even numbers printed from the multi, and obviously the single just returns a single value. Now the second example I have here is the web server. So I will make it, okay, now it looks big enough to be readable. And in this case, I have decided to make it a bit more complicated. So I have two routes on my web server. There is the /entry and /echo. And I'm creating a client as well, a reactive client. And now let's have a look on the routes, which is the important part. And I'm always looking at the wrong screen, so here. So the first route is simple. It just sends the data it gets. So it's an echo service. You post some data, it sends it back. The second route is more interesting. So here, when I get data, I actually post it over the client to the first endpoint. And the reason why I did this is really to show you the reactive program there. So I request a post, I submit data, where I send request.content. Now, request.content is a publisher of bytes, basically. That's what we get from the web server. That's the default value that you get. Then I map the result to the content of the response, which incidentally is a publisher of bytes. That's what you get by default from the client. And once I get this publisher, I send it on the response. Because the response.send in web server, one of the signatures is it accepts a publisher of bytes. So let me show you the API. So if I do response.send, you can see that one of the signatures that we have is a publisher of bytes. So this is a proper end-to-end usage of publishers from client to server and back to the original client. And one of the things, it looks great because this is the use case that we try to optimize for. Still, you know that this is not really the usual coding that we are used to. Normally, I would expect to have client.get on that path, give me the input stream, and then I would say response.output stream, and I would just copy the bytes over. So in reactive, everything works differently. You need to have the chain. One thing that is missing here, and this is like the biggest problem of the reactive, and you need to remember that really well if you want to ever write reactive code. I'm missing an exception handler. Now, if this happened in a blocking code, and my remote client failed, I would just throw an exception, and my client would get internal server error, a 500. Now, in this case, if I get an exception on the web client request, nothing happens, because my reactive stream is not finished. So what happens is, let's say the submit method throws an exception. That is propagated through the chain until the end, but there is nobody waiting for it. So it's not reported. What will happen from the point of the client? You will be waiting for your response indefinitely, or until you get a timeout. That's not a very good thing. So whenever using reactive, there needs to be one thing at the end where you need to write exceptionally. In our case, we again have a suitable method on our response where you can just write the exception to, and it will do the correct task. Probably it will do a 500 error with some descriptive text. It will probably log the message to a logger. But you need to do it. If you don't do it, you just lost your stream. You have no idea what's happening. Second problem with this is, let's say that you have a system and you know that something is blocked. You are waiting for your response, you don't know what's happening. So, you do a thread dump. And unfortunately, in reactive programming, a thread dump is absolutely useless, because your code is not there. It's not blocking anywhere, because you are forbidden to block. It's waiting somewhere, in probably native code, on a socket read. Who knows? But it's definitely not in Java. So troubleshooting of reactive, way harder than troubleshooting of blocking code. I know I'm always saying the complications, but you need to understand that, because reactive is just not for your hello world application. Reactive is for cases where you need heavily concurrent requests for no other. Okay, let's go back to the presentation. I will hope that it switches to the correct window. Yay. So now a bit into the things that help you coding reactive and where it actually makes a lot of sense. One of them is reactive messaging. Microprofile created a specification for that, which we are using, and we are actually using the same approach also in our Helidon SE. And here is exactly the part where it all makes sense. Because if you have Kafka sitting somewhere, it just streams messages to you. And you want to control that stream. You want to be able to say, please don't send additional messages right now. I'm busy processing your previous messages. So this is exactly where reactive streams shine and make a lot of sense. The whole API is basically allowing you to write methods where you just annotate them and say which channel you wait on messages for, or which channel you want to write to. I will not go into deep detail on that. You just need to know that it exists. And again, it's using, unfortunately, Microprofile is still supporting Java 8. So how many people use Java 8? Can I have a show of hands, please? Good, good. Don't use it. It's bad. Now, honestly, Java 8 is great. It was one of the best releases of Java in history. Unfortunately, it's also old. If you take a program written on Java 8 and just run it on Java 17, you can get like 40% performance increase just by running it on a newer version of Java. In Helidon, we threw away Java 8 a long time ago. Our version 2 runs on Java 11 as the minimal required version. Our version 3 will have 17 as the minimal required version, and version 4 will probably have Java 21 as the minimal required version. And there is a good reason for that. The language improves and is faster. You don't want to get stuck in history just because somebody says that it's not a good idea for whatever reasons that sound too much like legacy explanations why you want to use COBOL. I like that in the presentation at the beginning. You don't want to use COBOL either, right? So don't use Java 8. And back to the presentation. Java 8 does not contain Flow API. So Microprofile has to use reactive streams, which is a complication for us because you need to put that API to go from a reactive stream into Helidon reactive components and back. Luckily, it's not such a big problem because it's, in the end, just another subscriber. But somebody had to implement it. It's a library you need to use. Okay, so I will just skip all of these nice things. There is links where you can have a look how this can be used. And I want to go to Helidon Reactive Messaging for Helidon SE, programmatic. So our artifact ID that you can use to add reactive messaging. And again, it's based on channels. So channel is a named pair. You have a publisher, you have a subscriber, and in between, you can have a processor. So it maps very good to the Flow API. So the subscriber is the part that gets the messages in the end and does something with them, writing them to a file, sending them over the network, storing them to a database, whatever. Publisher is the thing that is the source of messages, Kafka, JMS, whatever you choose. And the processor is the part that makes sure that you transform the data from the original state to the state that is desired, like transforming them into a JSON object or making them a POJO that you can store into your database. So here's an example. You create a publisher and a listener. The publisher will be the source of data. The listener I don't know why it's called listener when it's a subscriber, but that's just the choice of the APIs. Talked about processor. A bit more convoluted test, but the important part here is that, again, on the top you have the publisher that sources the data, processor does something with them, subscriber takes the final result and executes it. So there is a message, and here just a note, Helidon SE is no magic, so we don't do magical acknowledgements, for example. In microprofile, if you consume a message, there will be some process happening in the background that will make sure that the message is acknowledged to the source. In Helidon SE, you need to take care of that yourself. Now, what I wanted to get to is the connectors. So we ship, as part of Helidon, connectors for Kafka, for JMS, like a generic JMS connector, and Oracle Advanced Queuing connector, which has some few features built on top of JMS. This is like Kafka is probably the most important if you are writing a cloud-native application. JMS is very useful when you are doing migrations. So one of the tasks that we have a lot of times is migrating from, and again, I will use the word legacy, application server into microservices. It really helps when you can talk to your application server. A lot of companies use WebLogics, JBosses, and so on. You want to be able to communicate with them. This is one of the ways how we can do that. So, messaging, the really important part, how to source your data, how to get them. Then you have your web server that will be making sure that you can get some requests from outside and run them. And then we are missing just the last part, which is how do I process the data? How do I store them? So I will go to my last section, which is the reactive goodies. So first thing that we built in Helidon is a reactive DB client. It's a reasonably simple abstraction for CRUD operations over databases, which supports both relational databases and non-relational databases. Right now, we have implementation on MongoDB because that's a truly reactive driver. So if you use Mongo, it will be all reactive all the way down to the very core of the database. If you use JDBC, then obviously we are stuck with non-reactive database drivers. So in that case, what we do, we wrap it in an executor service. So it is not reactive all the way down, but it's at least not blocking the threads of the server, because if you block the thread of the server in reactive environment, the server will die. Like, you cannot do it even for a while. Because, for example, if you run on my laptop, your server will be using 4 to 8 threads, and that's it. And if you block them, if you have one service that writes to the database directly within your request threads, your web server will stop accepting additional requests. So you will process exactly 8 parallel requests, and that's it. So you never block. And this is the way how you do it if you have a blocking backend. You create something that will create an executor service around it, and even though you are limiting yourself to the size of that executor service, at least you are not breaking your environment. So how does it work? It's configuration driven, sorry. So in your configuration, you define the connection to your database, and you also define your statements, which act as templates. You can use the classical JDBC approach of using question marks as a parameter placeholder, or you can use named parameter placeholders that we fill in from your request. And then you can do something like this. So you just say, DB client, please execute me this named query that is defined in the configuration, and map each row as a JSON object, and you get a publisher of JSON objects. So it's a truly reactive API, which for some data sources will be reactive to the database. For some data sources, it will be wrapped in an executor. So what is the next thing that you want to do? You want to call another service. Again, we have a web client, a fully reactive implementation. This time this is truly reactive all the way. So you can just do something like you see here. You can get a single of a JSON object by calling webclient.get, which is the HTTP method. You have the path. I'm actually expecting I have some kind of base URI that I configure at the beginning. And then you get request. Now, how does this work? Let's imagine you have a 1 megabyte JSON object. So the client will initiate a connection, do all the writes to the connection and expect some response. And when it gets, let's say that you have 100 buffers that are being sent over. So it will get each buffer, it will store it, until you get the last one. When you get the last one, it parses it into JSON, and you get your JSON object in the future. That's why you get a single as a result, because it's a promise of a future result. Obviously, the reactiveness here is limited, because I have chosen to use JSON object, which needs to be manifested in memory. If you used, for example, you wanted to write it to a response of a server, or you wanted to write it to file system, you can actually act directly on the byte buffers, and then you would just get for each of these 100 buffers that you get, you would do something with them like storing them, or you would flat map it to another single that will take care of that write. And I'm intentionally saying the complicated part, because sometimes you just need to do this. So this is an example of, I need to do something that's returning a future, and within that, I need to do something else that also returns a future or a publisher. And in that case, there are the flat map methods. So in this case, I'm flat mapping a single. So for each thing that I get, I'm expecting to just have a single result. You could also flat map to a multi. So if you want to do like HTTP request that returns an array of 5, and for each 5 you go to the database and get a result set of 10, you can also do it this way. You can flat map it into a single stream. And I'm going back to the thing I said before. You need to do it as a single stream, because if you break your stream anywhere and you start doing internal loops, they will be running in different threads. And first, you will be losing exceptions. And second, you may actually lose the continuity, and you may return before you complete. So very important, if you are writing reactive streams, you need to write them in a single statement that looks something like this and do something with your exceptions. And it looks still kind of okay-ish for this case, but if you have, like cycles within cycles, then you will be afraid of the code. So I still have time, so I will also show you the alternatives that we are working on right now. So before that, let's have a look on the things that you can learn more about Helidon. Our documentation is available. We have examples and guidelines. And let's get to the stuff I promised at the beginning, the future, what is actually being worked on right now. So reactive is hard, for sure. The payoff is also very good. You get something that cannot be beaten in concurrency in Java right now. So is there a way how we can do this without reactive? And again, I said you cannot do it right now. But fortunately, you can do it in the future. And the future is available as an early access release of Java 19. So, who has heard of Project Loom? Okay. In Java 19, luckily for us, they have merged the Project Loom, and it's available now as early access download on JDK. And Project Loom is the next thing in Java. Like, honestly, that's a breakthrough that we haven't seen before for a long time. Because Project Loom uses something that is called virtual threads. And the good thing for us, you don't need to really know about it, but I will tell you what's happening underneath the hoods. So if I have a virtual thread that's processing my web server request, And within this virtual thread, I decide to call an external service. So my thread is being executed, it's runnable, and then I go to this socket request. And in normal application, this would block your thread, and it would be waiting. But in Loom, the virtual thread is just parked away. The underlying platform thread continues to execute something else until you get some data from your socket. When you get the data from the socket, it revives your context of the virtual thread, and it just continues from that point on. You don't need to know about it. It just works. And because we really like it, and we don't like reactive programming, like we built a server that is based for it, but we know that that's not the right thing for a programmer. It's complicated to maintain. It's hard to troubleshoot. So we decided we will have a look at that. And what we did, we have written a web server that is fully based on virtual threads. And we ran some benchmarks against it. So in Helidon 4, we will definitely do a pre-release as soon as Java 19 is out. And this pre-release will be fully utilizing virtual threads. And what I hope is this will allow us to move away from reactive in the longer term. And we have to understand here, I'm talking about 2 years, probably. This is not something that will happen next week, because it's a preview feature in Java, so until you can use it in production, you need to wait until it's in actual long-term supported version of Java as a normal feature, which is probably going to be 21, fingers crossed. But we will be ready. I will show first, this is the same code we had there in that reactive stream before, written as a blocking code. And the great thing here is that if you put a for cycle there, who cares? You put a for cycle. If you throw an exception, the framework will catch it. This is a normal blocking code. So I see this as the breakthrough in Java, and I have last thing I wanted to show for this, and that's the numbers that we got from our benchmarks, because I really think they are interesting. So I will just need to do my magic with the different screens here. Okay, now, come on, move. There it comes, there it comes. It's a nimble work with the touchpad. I'm not used to that, sorry about. So what I want to show here is this. So the numbers that you see are comparing our virtual thread-based implementation with Netty, which is the current fastest HTTP server that you can get. And it's just different profiles. So we have, this is JSON processing. This is a single-threaded, basically you get a single request, you wait for a single response, and all the bigger numbers are using HTTP 1.1 pipelining, which means that you send multiple requests at the same time, and then you wait for the responses. These last two numbers are HTTP 2. So this is HTTP 2 with TLS. This is HTTP 2 with plain text. I will not say we are faster than Netty. Like, it's hard because they are doing as much as can be done, but we are at least on par with Netty. And if this works in our production release, like, this means that there is no need to use reactive. If the numbers will be more than 10% off, then the use cases still exist. But if we reach within 10%, I think that reactive doesn't need to be, in 2 years, in 3 years, it will be a decline of reactive coding because of this. So really, for us, this is where we see our future. And fingers crossed that Project Loom is successful and actually delivered as a production feature. And with that, thank you very much for your attention. And if there are any questions, either ask them now or you can come back later. We can talk about it before I leave. Thank you very much for your attention.